best-known symbol of the 1962 World's Fair in Seattle is the tallest structure west of the Mississippi River, steel rising 600 feet above the high-speed monorail train and the fairgrounds. The world has never before seen anything like the Space Needle. But in the spring of 1961, there was no graceful tower here. Just a Y-shaped excavation, 30 feet deep, and concrete pads to support the structure's huge anchor bolts. This was a scene less than a year before the opening of the World's Fair. Fabrication and erection of the amazing tower was the responsibility of the Structural Steel Division of Pacific Car and Foundry Company. Huge steel anchor bolts, over 30 feet long and 4 inches in diameter, were assembled in 12-rod units, and there were 6 of these anchorage assemblies in the structure. The bottom plates are 1.5 feet square and 3 inches thick. Moved from the shop out to the site, anchor bolt assemblies are lowered onto the concrete pads. You may also notice that the bolts are set at a slight angle, the same angle as the main leg of the tower, tipping slightly toward the center of the structure. Plans call for a continuous pour of concrete. After the anchor bolts and 250 tons of reinforcing steel are in place, 470 truckloads of concrete are poured in something over 12 hours. That's 2,800 cubic yards, the largest continuous building concrete pour in the West. Here, the anchor bolts stand after the first 12 feet have been poured. Even with 3,700 tons of steel in the tower, the foundation is so massive that the center of gravity of the entire structure will be very near the ground. Meanwhile, Pacific Car and Foundry Company shops are fabricating the steel core sections. With an extremely tight construction schedule, precision in the shop is a must. Everything has to fit. A template is used here to set the connection plates. The sheath-like design of the Space Needle is composed of a central core and 3 pairs of legs with a tapered hourglass waist. This is another core truss, ready for milling and painting. The sections are welded together in the field, but to be sure that they are set properly, the ends are milled to exact length in the shop. There are no changes in the field. 3 of these trusses make up the triangular core, and here one of the sections moves out to the site. Architects for the Seattle Space Needle were John Graham and Company of Seattle and New York. Structural design engineer was John K. Menashian of Pasadena, California, who has also designed steel structures for rocket launching pads at Cape Canaveral. And general contractor in the project was Howard S. Wright Construction Company. Even in the early stages of Space Needle construction, the deft skill of the iron workers fascinated Seattle's most experienced sidewalk superintendents. In order to avoid uneven expansion during this core section welding, one man works on the outside and another on the inside. Raising steel 600 feet in the air on a slender tower was a real problem. Pacific Car and Foundry Company designed a special derrick crane for the job. Now they're ready to put the jumping jack derrick in place. The core of the Space Needle is 68 feet above the ground at this moment. Much of the first section was set below ground. A thrust ring at the top provides stability for the mast. Down below is a bearing support on which the base of the derrick rotates a full 360 degrees. To distinguish the derrick and other tools of construction from the rest of the structure, they're painted a bright fire engine red. A 100-ton crawler crane with a 130-foot boom lifts all the steel until the climbing derrick is operating. When the mast is in place on top, they raise the boom. Here goes the outer section. The capacity of the derrick crane is 35 tons. The boom can be operated from a vertical to a horizontal position, as well as turned through a complete circle. Although the derrick goes into position at the 68-foot level, crews will continue to work with the ground crane till the 120-foot level is reached. Meantime, a specially designed hoist is built for this job and completed in record time before the tower runs away from the reach of the mobile crane on the ground. As they test the rotation of the derrick now, note how the operator uses a throat microphone to communicate with the hoist engineer below, and the boom swings round above him. Regular routine on the job calls for about 3 days of welding after core sections are in place. During this time, the raising crews set stairs inside the core. Now the special hoist gets ready to take over the lifting job. There's nearly 4,000 feet of cable on one drum. Specifications call for operating speeds from 11 feet to 400 feet per minute. But the ground crane is still working, raising core sections around the derrick until it's completely enclosed. When it's boxed in on all 3 sides, they're ready for the jump, and the derrick will lift itself up by its own bootstraps. During the course of Space Needle construction, the derrick is jumped about every 7 days. With a cable speed as low as 11 feet per minute and pulley reduction, it's possible to move steel gently enough to crack an egg without breaking it. Usually, it takes about 25 minutes to raise the derrick to a new position in the core. Watch it rise to the 120-foot level. Now the first of 6 main leg bases moves into place. Pointed sleeves on the anchor bolts protect the threads. You'll remember the anchor bolts, like the main legs, are set at a slight angle toward the center of the needle. Because of this, it's necessary to use a special lifting device to tilt the section at the proper angle to slide over the bolts. As usual, everything works like a charm. Rising with the tower, movable scaffolds slide up the legs and the core, a special safety feature on the job. And there's a landing platform every 30 feet on the ironworker's ladder. With no open space for a construction elevator until the project is much farther along, workmen ride up in the skip or climb the ladder. For the Space Needle's mighty tripod legs, United States Steel provided the largest wide-flange beams ever rolled. They're up to 90 feet long, produced from single ingots weighing 28,000 pounds. 3 of them make up a leg section. As you'll see in a few minutes, workmen have to get inside the leg sections to bolt and weld joints in the field. So a manhole is cut in the leg here in the shop. The I-beams are welded together flange to form the leg sections. A sealing strip is added on the outside as a backup bar for the weld and to keep the leg watertight. They're working 3 shifts in the shop now, and the yard is full of main leg sections ready to go. The tubes are stiffened with diaphragms on the inside at a maximum spacing of 10 feet. Here's how they turn the section so welders always have a down hand to weld. Like the core sections, legs go to the mill, and the ends are finished precisely before they're sent out to the erection crew in the field. Holes for the bolted joints are also drilled in the shop. The entire series is drilled at this time. To make sure of a fit in the field, joints are individually mated in the shop before each section goes out to the site. Temporary bolts hold the plates on one side, the undrilled section is moved in, fitted tightly, and then drilled. Now the 90-foot leg is on its way to the needle. 47 tons of steel in one piece. This first section is raised and held by the crane on the ground while the derrick sets the tie-back box girder to the core, thus avoiding the need for any guy lines. But after these first legs are in place, the jumping derrick will have to handle the whole lifting job by itself. Besides precision in the shop, there's a constant check on construction in the field. Because steel moves just a little with the heat of the sun, the tower is checked for plumbness early in the morning, as soon as it's light enough to see. Step by step, the work progresses without a hitch. Fabricated steel moves out of the shop to the site on schedule. Everybody on this job knows there's a deadline to meet, and everybody takes a special pride in showing the world that it can be done. Thanks to the efforts of all, there are no real troubles except the weather. Members go into place and fit just right. Even the weather didn't cause too much delay. Crews usually found some way to keep the project moving. Now they're up to the 200-foot level, and another leg section goes into place. As you watch the work in progress, you'll see how the workmen use the manholes that were cut in the shop, working inside both legs and girders. At least 20 men are assigned to the work of bolting joints. And before the Space Needle is finished, they'll use 52,000 one-inch bolts and 22,000 three-quarter-inch bolts, 74,000 in all. The last operation after bolting is welding the plate back into the access hole. Anybody who wants in after that will have to cut his way in. Now the shop is working on the curved legs that move in at the waist of the needle. Each individual beam has its own compound curve. Pacific Car and Foundry Company solves the difficult problem of forming the curves by placing the beams in a simple marked jig fixture and heating wedge-shaped portions of the steel. This causes the material to upset. You can see the heat waves rising from the beam. When the steel cools, the wide part of the heated section shrinks the most and curves the beam. It takes the skillful touch of experienced steelmen to do the job, but when the curved beams are assembled, they fit together just as neatly as the straight beams did. Now the steel diaphragms are in, and they're working on the finished welding. Soon the curved legs are ready to go out to the job site. It's a tricky job for the erection crew like this one. Even a moderate breeze can make the steel spin like a spoon on a fisherman's line. But with the air calm, everything goes smoothly, and the curved leg is swung into position, forming the waist of the needle 373 feet above the ground. Just beyond the waist, the legs flare out and change from 3-beam triangular to 2-beam box construction. Here in the shop, a transition leg is joined at the point where the box section begins. The field crew has the same kind of problem with this section as with the curved legs. Even a slight breeze can cause trouble. So they begin the lift at 5 a.m. in the dead calm of early morning. High winds can stop all crane work anytime, but no other job for the lifting crew is quite as ticklish as raising a load like this. Inevitably, Seattle's famous Space Needle has been compared with the Eiffel Tower of Paris. Both were built for expositions. Both have become symbols of a city. Both are a steel construction. But the steel of the Eiffel Tower was joined entirely with rivets, 2.5 million of them. Only bolting and welding is used in the Space Needle. And here you get some idea of the tremendous number of high-tensile bolts used in the construction. When the welders do what is known in the trade as back gouging, it makes a spectacular show. Meanwhile, the fabricators assembled a ring girder for the Space Needle restaurant. After shop assembly, small sections from the ring will be joined with the top leg sections. Midway in fabrication and erection, the needle's color scheme has been set, and most members are now going out to the site with their final finish. This box leg is almost 80 feet long and the most difficult lift of all for the derrick. These sections flare out at the top like 6 fingers holding a saucer, and the crane has to work with a boom almost flat. The tower is now at the 500-foot level. Turnbuckles on 1 1/4-inch rods are raised and guide the section to the core, holding the leg in place until a box girder is raised and set. With only one crane, they can't handle the job as they did with the long first leg. Here again is a small segment of the restaurant's ring girder attached to the top of one of the main support legs. And now, it's about time for a cigarette. While a high wind can stop everything, work proceeds as usual on a rainy morning, as you can see. Box girders move in for a permanent connection between the final leg and the core. And when 2 of the legs are in position, a ring section is placed between them. Outriggers for the revolving restaurant floor are assembled with a ring section on the ground. It takes 6 sections like this